So today's problem of the day is superprimes. A prime number is superprime if it is a sum of two primes. Okay, find all the superprimes up to n. So if n is equal to 5, we have only one superprime, that is 5, which is equal to 2 plus 3, and this 2 is a prime number, 3 is also a prime number. So if we have a prime number which is the sum of two other prime numbers, then that particular number is said to be superprime. That is what we call as superprime. Now we have another one, n is equal to 10. Okay, so between n, like what are the different prime numbers? We have 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number. So 5 can be obtained as 3 plus 2 and 7 can be obtained as 5 plus 2. So answer is just 2. We have only two numbers. So how can we do this? So one thing to notice, what are all the prime numbers that we are having? Forget about any n, don't consider n. What are the different prime numbers we are having? We are having 2, we are having 3, 5, 7, then what, I think 11, 13, 17, 19, etc, etc. And what about how many odd numbers or how many even numbers within all these prime numbers? That's the key for solving this problem. That's the only observation that we require in order to solve this problem. Here we can only see that 2 is the only prime number which is even and all the others are odd. So all the others are odd. Now our question is, we are having some value x which is equal to y plus z, and y and z is both prime number and x is also prime number. Okay, keep that in mind. Now we have, suppose we have 3, we are taking one odd number, only one even number we are having as a prime number and all the others are odd. So what is odd? An odd number plus odd number. Odd number plus odd number is surely an even number, and this will never be a prime number because we are only having 2 as the prime number, and we will not be able to get 2 as a super prime because 2 is the very first prime number that we are having, and there are no other two prime numbers which when we add together will gives us 2. Okay, so odd plus odd is not possible. The only possibility is odd plus some values. Okay, odd plus 2. So if we find an x which is equal to some odd number plus 2, then x is a prime number. So we need to check for each and every number, say for each and every number n, we need to check. So this is simple. So for each and every number, let me increase it. Okay, so for each and every number, say current number Cn, we just need to check whether Cn is prime and Cn minus 2 is prime. Only that what we need to check, because we will be adding 1 with 2. 2 is already a prime number. Then we are adding with some y which is equal to z, and we need to make sure this z is a prime number. And what is y? Y is equal to z minus 2. So z is the current number. Okay, z is the current number, and we need to make sure that z is a prime number, and we also need to make sure z minus 2 which is equal to y is also a prime number. If both of these conditions occur, then we are having a super prime. We just increase the count. So here like we all know, we can just go with the traditional way of finding whether a particular number is prime number or not. But there is also like a CU method in order to find a particular number is prime or not. For that, like we'll be having a boolean array. And in this boolean array all the prime numbers will be false. For example, 2 will be false, 3 will be false, 5 will be false, etc. And all its multiplications starting from 2 into 2, which is equal to 4. This is not a prime number because it's having a factor of 2, 4 and 1. So this will be marked as true. Same way 3 into 2, which is equal to 6, will be marked as true. Also 3 into 3 equal to 9 will be marked as true. All these are not prime numbers. So we will be tracking those inside a boolean array, and this is what we call a sieve method. Sieve of Eratosthenes, I think. I don't know about the correct pronunciation. Sorry if there is any error. So that's the way that we will be doing the problem now. So as told, we need to track prime tracker, which is equal to new boolean of n plus 1, because we need to include n up to n. Now let's have a sieve helper method in order to fill our prime tracker. Now after the prime tracker gets filled, we just need to find, for int I is equal to 5, we can just start from 5, I less than or equal to n, I plus plus, if prime, if it is prime, then it is marked as false. So if prime tracker of I, so if it becomes false, that means that particular number, the current number, is prime. And what the other number, what I told, like 2 plus y, one number will always be true. Sorry, one number will always be 2. Okay, like there is only one even number that we are having, 2, and all the others 2, 5, 7, take any other prime number, it will be odd. And if we take two odd prime numbers, its sum will be an even, and that even number will never be another super prime. So the only possibility that we are having is with 2, and if this 2 plus y is equal to set, so one number will be 2, it will be fixed, and plus some other prime number will give a super prime. So we need to confirm, like the current number is a prime plus current number minus 2 is also a prime. That means 2 plus that number is equal to a super prime. So not prime tracker of I minus 2. That's the case, we increase our count. So we also need a count, int count is equal to 0 and return count. What if our n is equal to 1? If our n is equal to 1, we are not having any prime number, we will not be able to find any value. So if n is less than or equal to 4, we will not be able to find any. Now we have a helper function that we need to fill. So boolean prime tracker, this tracker will be tracking all the prime numbers. So for int I is equal to 2, I into I is less than or equal to n, I plus plus, if it's a prime number, if not prime tracker of I, then we will be tracking all its multiplications, like that prime number into 2, that prime number into 3, that prime number into 4, that prime number into 5. All it will be marked as true, which means it is not a prime number. So let me write prime tracker of I equal to false means I is prime. True means I is not prime. So if it is a prime, then we will be marking all its multiplications. So for in j is equal to 2, j into I is less than or equal to n, j plus plus prime tracker of I into j is marked as true. So what's the time complexity? So time complexity, this sieve will be having a time complexity of big O of n into log of log n. Okay, here we are having a log, Okay, n into, here we are having a log into a log here, so n into log of log n. So that's our time complexity, and here also, so big of n into log n plus big of n, you can say the total time complexity is big of n into log n. And the space complexity, we are making use of a boolean prime tracker of length n maximum, so big of n is the time complexity, sorry, big of n is the space complexity. So just a brief, the time complexity will be big of n into log of log n, n into log of log n, and space complexity will be big of n. Okay, just compile. I think there are no errors, I didn't catch any. So okay, what if we give large number? That's also fine, and we are submitting. Okay, so that's it. The key point is there is only one even number in all the list of the primes that we are having, and all the others are odd. Two odd numbers when we added will only give even number, but we are only having one even number as a prime, that is 2. So there is no possibility that in order to get a super prime we need to add two odd numbers. There must be an even number, so that even number we are having is 2. So one of the number is surely 2. So 2 plus one prime number is equal to super prime. So that super prime must be a prime number, and that super prime minus 2 must also be another prime number. So just make use of sieve method, or the normal checking of the prime will also will do, I guess. So at that time, like, it will be big of n into root of n, kind of a complexity, I guess. So that's today's problem, super primes.